part 2 for section 10.1. So we left off with the translation, the slide. Now we're going to look at a rotation. So a rotation of an object moves the object around a point called the rotocenter a certain angle theta, either clockwise or counterclockwise. So clockwise, you're moving this way. Counterclockwise, you're going that way. And the rotocenter can be either inside or outside the shape. So for inside, kind of picture like a wheel spinning around the axle, and well, the axle moves with it, but picture that rotocenter is actually inside the wheel. It's rotating with that axle in the center. And outside the shape would be something where you maybe have a stick with a string and something at the end of that string, and you start spinning the shape around the string. Even though you're going to have to move that stick to get it to do that. Imagine that stick was fixed and that object was stretched out on the string and then just moving around. Might even want to think of like tetherball, if anybody ever played tetherball. The ball would be the object moving around the rotocenter, which was the pole that the ball was tied to. That takes me back. Lots of tetherball when I was a kid. Okay, so anyway, you can either be inside or outside with that rotational center, the rotocenter. So for example here, we're going to rotate the figure 90 degrees clockwise about the rotocenter. So 90 degrees clockwise, I'm going to pick this point up here. And actually I'll pick one closer, it's a little easier to draw. So I'm going to pick that point right there, I'll call that A. And I'm going to move it 90 degrees clockwise. So come over to here, and it would come right down to there. This point up here, if we rotate it 90 degrees, will end up right here. And then this point, if we were to rotate it 90 degrees, would end up down here. And just check that that's 90. If you connect here, you see that's a 90-degree angle. So the shape then gets drawn in like this, and that is your rotation about that rotocenter R for that particular triangle. And in this case, the rotocenter is outside the shape. So some properties of rotation. It's completely determined by 2 points, P and P prime. So here we'd have A go to A prime, and the whole rest of the shape comes with it. It has one fixed point, the rotocenter R. So that rotocenter never moves. Things move around it, but the rotocenter itself doesn't change position. And it has an identity motion, the 360-degree rotation. If you rotate 360 degrees, you've gone one full circle and come back to where you started. So that would be the identity motion. Okay, a reflection. This one's got a lot of words to it, and I'll draw a little picture after we go through it. But if each point on the line L corresponds to itself, so it's just this line L that doesn't move, basically, each other point P in the plane corresponds to a unique point P prime in the plane, such that L is the perpendicular bisector of the segment PP prime. That's a whole lot to take in, but let's draw this. So here's my line L that corresponds on all the points on the line L correspond to itself. These points aren't going to move. They're just staying right where they are. So this is my line L. And then if I had some point over here, point P, and then there will be a perpendicular bisector between it, or I should say, it will be perpendicularly bisected by L if I connect it to P prime. So all this really means is that the distance on this side is the same as the distance on that side, bisected by L, and it's perpendicular to L, which means that it's a right angle. So for these reflections, if you draw a line segment between the point and its image, the L will be the perpendicular bisector of that. Another way to look at this is like, oh, we started over here. I'm going to go to the line and then go that exact same distance on the other side of the line. And I want to make sure that I'm hitting that line at a right angle. I want to travel the shortest distance to get to the line, which would be meeting at a right angle. So the correspondence when these conditions are satisfied is called a reflection. These are also known as flips. You know, if you flip P over line L, you end up at P prime. That's another way they'll talk about it. So let's see this in an example. So I want to reflect over the line L. So I'm going to start down here with this point, and I'm just going to go at a right angle to hit the line, and that's one diagonal worth of box, so I'll end up over here. And if I were to do that, it's a rigid motion, the whole shape should come over there, but if you're like, I can't really see where the rest would go, I'll move a couple more points. So I'm going to take this point, diagonal 1.5, so then 1/2 and 1, take me to right here. Again, you're always hitting the line at a right angle. Maybe this one up here, we go here, 1, 2.5, 1/2, 1.5, 2.5 to here, and then that pretty much should be enough because this side here is 2, so it's going to end up here, 2 length, and then we can start filling in the rest of the shape. This is a little bigger here than a full box. You know, I'm looking at this side right there, and then we come over, and that's not quite good, but good enough for hand drawing. And then you can look at this after I fill this in and get a sense that, oh yeah, this thing has been reflected. It looks like a mirror image on the other side of that line L. And that's what you're really looking for, a mirror image. Okay, so that's a reflection. And the properties, it's completely determined by 2 points, P and P prime. If I could take that little L-looking shape that I got there, that blue solid shape, pick it up and flip it over the line, you know, just grabbing one corner, the whole shape's going to come with it. So it's still, you just need 2 points to determine it. And then it has infinite fixed points, the line of reflection L. This line of reflection doesn't move. Any point that's on there is fixed. And there's a whole bunch of them, infinite, because of those arrows going all the way up, all the way down, tell me a line goes on forever. The identity motion is just a reverse reflection. So if I was up here in this thing that I drew and then reflected it back, I'd get back to where I started. That's about it for reflections. The glide reflection, this one's kind of crazy. It's got a little bit of trickiness to it. Glide reflection, it's a combination of reflection and translation. And in order to get these correct in the online homework, you have to do the reflection first and the translation second. If you don't do that, you will get the wrong answer. It's very, very picky. And in reality, if the vector of motion here for your glide or slide is the same direction as the line, it doesn't matter what order you do these in. But when the line and the vector are not parallel, order matters. And what you're going to see again is that you need to reflect first and then slide if you're going to get to the right answer. You know, if you don't do that, it's not going to work. So just keep that in mind. It's a little picky, and you got to do reflection and translation. Can't stress that enough. So here, let's mimic the steps in this paper. So I'm going to reflect first. So this shape, I'm going to take this point here. It'll end up over here. This point's on the line, so it'll stay. And I have a box that's 2 wide by 3 tall, so when I reflect it, it'll become 3 long, which will be roughly right there. I don't know why that box is weird like that. But we would have a shape like this for the reflection. So the reflection is first. Then we will slide. And in this case, we're sliding parallel to the line. 2 units diagonal. So it will come down here and end up right here roughly. So this would be the final shape. That reflection, it's kind of like a pit stop, like you reflect, pause, take your breath, and then you slide to get to the final translated position. So if this was point A, it reflects up to here and then slides to here, this would be A prime. All right, so that's a glide reflection. They should call it reflection glide, but I don't think that rolls off the tongue as well, so they call it a glide reflection. And the reason they should call it reflection glide, you got to reflect first, then translate second when the line and the vector of motion are not parallel. And you'll see that all over the place in the homework. Okay, so properties of the glide reflection. A reflection is completely determined by 2 points, P and P prime, just like all the rest of these rigid motions. You move 1 point, the whole rest of the shape comes with you. And then it has infinite fixed points, the line of reflection, just like the reflection had the infinite fixed points on its line. Glide reflection has a reflection, so it should make sense. The fixed points are there. And the identity motion is the reverse glide reflection. So if you undid the slide and then undid the reflection, you would get back to where you started. And that's basically it for these 4 that we're looking at in this class. You got your glide reflection, you got your reflection, you have the rotation, and then you had the slide or the translation. So one thing to keep in mind with the homework for this, you can either click on a point, a corner, and move 1 point, which will be useful in some of the cases, or you can click on a side and you'll see the point will glow red or the side will glow red. And when you click on a side and start moving the shape, you'll notice the whole shape moves with you as a rigid motion. When you just click on a point, it only moves the 1 point. And it's a little disconcerting because the shape will get all distorted when you move 1 point. So what I would recommend is maybe sketch this out on paper and then make sure that you move the points in such a way that it matches what you drew on paper. That would be one way to maybe keep things straight and keep the end goal in mind, because it can be a little wonky when you're doing these. I will just warn you about that now. But otherwise, if you have questions about this, please ask and I will help you.